1920, San Joaquin Valley, California. The engineering consensus from major construction firms would never account for what happened in that dusty farmland that summer. Three-man scraper crews, tractor driver, blade operator walking alongside, coordinator managing loads, moving 40 cubic yards of earth per day at $12 per acre. European-trained engineers had declared single-operator earth moving mechanically unsound. The precision required for blade depth, the split-second timing for efficient loading, the coordination between cutting angle and forward motion, impossible for one man to control simultaneously. Traditional crews with proven methods, manual blade adjustment, physical coordination between multiple operators. Results that major construction companies could predict and budget. Then a sixth-grade dropout named LeTourneau welded electrical cables to a scraper blade and powered them with a small generator mounted on his tractor. While established contractors calculated crew wages and equipment maintenance, this mechanic was installing telescoping bowls that extended 4 feet for loading, retracted for transport, all controlled from the driver's seat. 800 miles from European engineering schools, the most decisive earth-moving revolution in construction history was taking shape. Not in superior manpower, not in bigger machines, but in electrical automation that would connect one American operator to mechanical power in ways traditional methods never imagined possible. The failed prototype sat in LeTourneau's garage like a mechanical corpse, its burnt electrical cables dangling from the scraper blade like severed arteries. 3 months of development had produced nothing but a machine that seized up in dust, shorted out in morning dew, and left him with exactly $47 between bankruptcy and his next experiment. The established contractors who had initially shown polite interest now crossed the street when they saw him coming, their skepticism vindicated by the smoking wreckage of his first attempt at electrical earth-moving control. LeTourneau loaded the damaged scraper onto a flatbed truck in the pre-dawn darkness of February 15, 1921, and drove 30 miles east to a 5-acre plot he had purchased on the outskirts of Stockton with his remaining savings. The land came with a corrugated metal shed, a concrete foundation, and access to Pacific Gas and Electric's new rural power lines, everything he needed to rebuild his vision from scratch. By noon, he had cleared workbenches along the shed's eastern wall and begun dismantling the failed prototype with methodical precision, laying each component on numbered canvas tarps like a surgeon preparing for the most critical operation of his career. The core problem revealed itself immediately as he examined the burned-out motor housings: dust infiltration. The San Joaquin Valley's fine alkali soil had penetrated every seal, creating conductive paths that turned electrical insulation into fire hazards. Traditional motor designs assumed indoor operation or at minimum protection from direct exposure to abrasive particles. LeTourneau's application demanded motors that could operate in conditions that would destroy conventional electrical equipment within hours. He needed to fundamentally reimagine how electrical power could survive in the agricultural machinery environment that European engineers had never encountered. Working 14-hour days through the winter of 1921, LeTourneau developed his waterproof motor housing system. Each motor was enclosed in a welded steel case with rubber gasket seals at every junction point. Fresh lubricating oil circulated through copper cooling lines, carrying away both heat and contaminating particles before they could damage the electrical windings. The cable systems received similar protection, armored conduits that could flex with the scraper's movement while maintaining complete environmental isolation. Every electrical connection was sealed in rubber compounds that LeTourneau mixed himself, testing dozens of formulations until he achieved complete moisture resistance. The telescoping bowl mechanism demanded even greater innovation. LeTourneau's vision required 2 nested steel sections that could extend 4 feet beyond their retracted position, creating a loading capacity that dwarfed traditional fixed bowl scrapers. The engineering challenge was immense. The extending section had to maintain structural integrity while supporting tons of earth, then retract smoothly for transport without jamming under load. European engineers had dismissed such mechanisms as inherently unreliable, arguing that the additional complexity would create multiple failure points that would strand machines in the field. LeTourneau solved the telescoping problem through precision manufacturing that surpassed anything available in commercial earth-moving equipment. He machined the nested steel sections to tolerances measured in thousandths of an inch, creating sliding surfaces that moved smoothly despite carrying massive loads. Bronze wear strips prevented steel-on-steel contact, while grease fittings allowed continuous lubrication of all moving surfaces. The extension and retraction were controlled by twin electric motors operating through a reduction gear system that provided enormous mechanical advantage. A single operator could extend or retract the bowl with finger pressure on a dashboard switch. The completed machine that emerged from LeTourneau's Stockton workshop in April 1921 bore no resemblance to conventional scrapers. 6 cubic yards of earth could be loaded in the extended position, twice the capacity of standard 3-yard units. The all-welded construction eliminated the riveted joints that loosened under stress, creating a structural integrity that could withstand forces that would destroy traditional equipment. Most revolutionary was the 500-amp generator system mounted behind the tractor cab, feeding electrical power to motors that controlled blade elevation, bowl extension, and cutting angle with precision that manual operators could never achieve. Abraham Grunauer's ranch job became the proving ground for LeTourneau's rebuilt vision. The German immigrant had contracted to level 30 acres of rolling pasture land for irrigation, a project that traditional crews estimated would require 3 weeks with standard equipment. Grunauer agreed to test LeTourneau's machine on a trial basis, 1 day of operation to demonstrate whether electrical controls could match manual precision in actual field conditions. The stakes were absolute. Success would validate LeTourneau's entire approach, while failure would confirm the engineering establishment's dismissal of single-operator earthmoving. The test began at 7 o'clock on a clear April morning. LeTourneau positioned his scraper at the high end of Grunauer's first field and engaged the electrical controls. The telescoping bowl extended to full reach, while the cutting blade automatically adjusted to optimal soil penetration depth. As the tractor moved forward, the blade sliced through earth with mechanical consistency that human operators could never maintain, while the extended bowl gathered maximum material with each pass. When the bowl reached capacity, LeTourneau retracted it with the flip of a switch and transported the load to the designated dumping area, where another switch command spread the earth with even distribution. By mid-afternoon, the results spoke with mathematical clarity. LeTourneau's single operator had moved 150 cubic yards of earth, triple the output of traditional 3-man crews. The electrical controls maintained consistent blade depth and cutting angle throughout the day, eliminating the human variations that reduced efficiency in manual operations. The telescoping bowl mechanism operated flawlessly, extending and retracting hundreds of times without jamming or mechanical failure. Grunauer watched the demonstration with the calculating eye of a man who understood exactly what he was witnessing, the obsolescence of every earth-moving method he had previously considered reliable. Word of LeTourneau's success spread through the San Joaquin Valley with the speed of agricultural gossip. Contractors who had dismissed electrical controls as impractical began inquiring about demonstration schedules. Equipment dealers who had refused to consider LeTourneau's prototypes suddenly expressed interest in distribution agreements. The mechanical revolution that European engineers had declared impossible was proving itself in California soil, 1 cubic yard at a time. The success at Grunauer's ranch created a problem LeTourneau had not anticipated, demand that exceeded his ability to build machines. By May 1921, 7 contractors had placed orders for his electrical scraper systems, while his Stockton workshop could produce only 1 unit every 6 weeks. The solution demanded expansion that would either establish LeTourneau as a legitimate manufacturer or bankrupt him attempting to meet commitments beyond his capacity. He mortgaged the Stockton property, borrowed against his future contracts, and hired Dutch Hendricks as his first full-time employee, a former railroad mechanic whose welding skills matched LeTourneau's exacting standards. Working through the summer of 1921, LeTourneau and Hendricks developed the manufacturing processes that would transform handcrafted prototypes into production machinery. The telescoping bowl mechanism required jigs and fixtures that could maintain thousandth of an inch tolerances across multiple units, while the electrical systems demanded quality control procedures that eliminated the field failures plaguing early prototypes. Each motor housing was pressure tested for waterproofing, Every electrical connection was inspected under magnification, and the generator systems underwent 48-hour endurance testing before installation. The result was manufacturing precision that exceeded anything available in agricultural equipment production. The breakthrough that would define LeTourneau's legacy emerged from an ambitious contract offered by the California State Highway Commission in June 1922. The Stockton to Tracy Highway project required cutting a roadbed through rolling terrain that traditional crews estimated would demand 3 months of intensive labor. The state offered a premium rate for early completion, $7 per 100 cubic yards if the work finished within 6 weeks, versus the standard $4 for conventional scheduling. LeTourneau calculated that his electrical controls could complete the project in 5 weeks, generating profit margins that would fund expansion of his manufacturing operation. The machine LeTourneau designed for the highway contract pushed every component to maximum capability. The mountain mover, as he named it, featured an 8-foot cutting width that doubled the earth-moving capacity of his previous designs. The all-welded construction utilized steel specifications borrowed from railroad bridge engineering, creating structural strength that could withstand forces that would destroy conventional scrapers. The 500-amp generator system was upgraded to deliver consistent power under the continuous operation that roadbed cutting demanded, while the motor housings incorporated cooling fins that dissipated heat generated by sustained high-output operation. The telescoping bowl mechanism achieved engineering sophistication that amazed even skeptical observers. The nested steel sections extended 6 feet beyond their retracted position, creating a total bowl length that could gather earth from an area twice the width of the machine itself. Bronze-bearing surfaces eliminated metal-on-metal contact between the sliding sections, while precision-machined guides maintained perfect alignment under loads that reached 8 tons per cycle. The extension and retraction were controlled by twin 15-horsepower electric motors operating through reduction gearing that provided mechanical advantage ratios of 20-to-1, allowing instantaneous response to operator commands while maintaining enormous pulling power. The electrical control system represented innovation that European engineers had never imagined possible in field conditions. Dashboard-mounted switches controlled blade elevation with precision measured in quarter-inch increments, while rheostat controls allowed infinite adjustment of cutting speed and transport velocity. The telescoping mechanism could extend or retract in 12 seconds, timing that eliminated the delays inherent in manual operation. Most revolutionary was the automatic load sensing system, electrical relays that detected when the bowl reached capacity and signaled the operator through dashboard indicators, eliminating guesswork and maximizing efficiency on every loading cycle. Highway construction began on July 8, 1922, under conditions that tested every component of LeTourneau's design. The rolling terrain demanded continuous blade adjustment as the scraper encountered varying soil conditions, while the production schedule required operation from dawn to dusk 6 days per week. Traditional crews working parallel sections provided direct comparison. Manual blade operators struggled to maintain consistent cutting depth, while their fixed bowl scrapers required multiple passes to gather the earth that LeTourneau's telescoping system collected in single cycles. The difference in productivity was immediately visible to Highway Commission inspectors who had never witnessed single-operator earth moving. By the end of the first week, LeTourneau's advantage was undeniable. The mountain mover had completed 800 cubic yards of roadbed cutting, while comparable traditional crews managed less than 300 yards. The electrical controls maintained precision that human operators could not match, cutting the roadbed to exact grade specifications without the variations that required costly rework. The telescoping bowl mechanism operated flawlessly under continuous use, extending and retracting thousands of times without mechanical failure or loss of precision. Highway Commission engineers who had initially viewed electrical controls with skepticism began studying LeTourneau's operation with the attention normally reserved for major engineering innovations. The breakthrough moment came during the 3rd week of construction when the mountain mover encountered a section of hardpan that had stopped traditional crews completely. The compacted earth layer, formed by decades of mineral deposition, could not be penetrated by conventional scraper blades without pre-braking using separate equipment. LeTourneau's electrical controls allowed precise blade pressure adjustment that could gradually work through the hardpan layer, while the powerful electric motors maintained consistent cutting force that manual operators could never sustain. What should have been a project-stopping obstacle became merely another demonstration of electrical control superiority. The final statistics validated every aspect of LeTourneau's revolutionary approach. The Stockton to Tracy Highway section was completed in 4 weeks and 3 days, 11 days ahead of schedule and 2 weeks faster than traditional methods. The total earth movement exceeded 2,400 cubic yards at a cost of $3.50 per 100 yards, less than half the expense of conventional crews. Highway Commission officials immediately approved LeTourneau for future state projects, while private contractors began placing orders for the mountain mover design. The mechanical revolution that began in a Stockton workshop had proven itself on the scale that mattered most: major infrastructure construction where precision, speed, and reliability determined success or failure. The success of the Stockton to Tracy Highway project created opportunities that dwarfed anything LeTourneau had previously imagined. Samuel Peterson, the San Francisco financier who had monitored the highway construction with calculating interest, arrived at LeTourneau's workshop in August 1922 with a contract that would either establish electrical earth moving as the industry standard or destroy LeTourneau's reputation permanently. The Central Valley Irrigation District needed 640 acres of farmland leveled to precise grades for a gravity-fed water system, work that traditional methods would require 6 months and cost over $60,000 in crew wages alone. Peterson's proposition was brutal in its clarity: complete the leveling in 30 days at $11 per acre, and LeTourneau would earn sufficient profit to expand his manufacturing operation statewide. Fail to meet the deadline and face a $15,000 penalty clause that would bankrupt his company and validate every skeptic who had dismissed electrical controls as unreliable under pressure. The mathematical challenge was staggering. 640 acres demanded moving over 30,000 cubic yards of earth, with tolerances measured in inches across terrain that varied by 12 feet from highest to lowest points. LeTourneau accepted the contract on August 23rd, committing to specifications that required precision beyond anything previously achieved in agricultural earth moving. The irrigation system demanded grade accuracy within 2 inches across the entire project area, while the 30-day deadline meant averaging over 20 acres per day of completed leveling. Traditional crews using manual controls had never approached such production rates, while the precision requirements exceeded what human operators could maintain over extended periods. LeTourneau was betting his company's future on electrical automation performing at levels that established engineering wisdom considered impossible. The project began with methodical surveying that revealed the true scope of the challenge. The 640 acres contained natural ridges rising 8 feet above the target grade, while depression areas required fill that would test the structural limits of any earth-moving equipment. The soil conditions varied from sandy loam that loaded easily to clay sections that could jam conventional scraper mechanisms. Most demanding was the irrigation district's requirement for consistent 2% slope across the entire area, mathematical precision that would drain surface water efficiently while preventing erosion during heavy rainfall periods. LeTourneau deployed 3 mountain mover units for the project, each operated by crews trained in electrical control techniques that bore no resemblance to traditional earth-moving methods. The telescoping bowl systems could extend to gather maximum earth from cut areas, then retract for transport to fill locations with timing, coordinated by electrical controls rather than human judgment. The blade elevation systems maintained consistent cutting depth regardless of operator fatigue, while automatic load sensing eliminated the guesswork that reduced efficiency in manual operations. The coordinated operation of 3 electrical units promised productivity that no combination of conventional equipment could match. The first 2 weeks exceeded every projection for electrical earth-moving efficiency. The 3 mountain movers operated in coordinated patterns that maximized earth movement while minimizing transport distances, with electrical controls maintaining precision that allowed operators to work extended shifts without accuracy degradation. The telescoping mechanisms extended and retracted thousands of times daily without mechanical failure, while the waterproof motor housings eliminated the electrical failures that had plagued earlier prototypes. By the end of week 2, over 400 acres had been completed to irrigation district specifications, placing the project 11 days ahead of schedule. The catastrophe struck without warning during maximum production on September 15th. The lead mountain mover was cutting through a section of particularly dense clay when the main generator began producing irregular voltage, causing the blade motors to operate erratically. LeTourneau shut down the machine for inspection, discovering that the generator windings had overheated under continuous high-output operation, causing insulation breakdown that would soon lead to complete electrical failure. Before repairs could begin, the damaged windings shorted catastrophically, igniting an electrical fire that destroyed the generator housing and damaged the telescoping mechanism's motor controls. The scope of the disaster became clear as LeTourneau assessed the wreckage. The burned generator could not be repaired in the field, while replacement parts required manufacturing time that would extend far beyond the contract deadline. The telescoping mechanism was mechanically intact but electrically inoperative, reducing the mountain mover to a conventional fixed-bowl scraper with fraction of its original capacity. Worse, the remaining 2 units were showing similar signs of generator stress, threatening total project shutdown just as the most demanding work remained incomplete. The irrigation district's engineers, who had gathered daily to observe the electrical revolution, now watched LeTourneau's reputation disintegrating in real time. The financial implications were devastating beyond the immediate contract penalty. Word of the electrical failure spread through the San Joaquin Valley construction community with the speed of confirmation bias. Established contractors who had resented LeTourneau's success celebrated the inevitable collapse of untested technology. Equipment dealers who had shown interest in electrical controls withdrew their inquiries, while potential customers who had planned future contracts began seeking traditional alternatives. The mechanical revolution that had seemed unstoppable just weeks earlier now appeared to be a dangerous experiment that failed when subjected to real-world demands. James Morrison, the Cornell-trained engineer representing Maritime Construction Company, arrived at the project site on September 18th to document the failure for his Boston headquarters. Morrison's report would influence major construction firms throughout the eastern United States, either validating electrical earthmoving as legitimate innovation or dismissing it as California eccentricity, unsuited for serious engineering projects. He examined the burned generator housing with the methodical attention of someone whose professional reputation depended on accurate technical assessment, while LeTourneau watched his life's work being evaluated by the engineering establishment that had always doubted electrical automation's viability. The irrigation district's patience was approaching its limit as unharvested acres awaited completion and autumn rains threatened to flood unleveled sections. Traditional contractors who had lost the original bid began contacting district officials with offers to complete the work using proven methods, while Samuel Peterson faced mounting pressure from his San Francisco investors who demanded explanation for their association with experimental technology. The 30-day deadline that had seemed achievable with electrical controls now appeared impossible to meet, while the $15,000 penalty clause loomed as the death sentence for LeTourneau's manufacturing dreams. The wreckage of the mountain mover's generator housing revealed secrets that would transform electrical earthmoving forever. Working by acetylene torchlight in his field workshop through the night of September 18th, LeTourneau discovered that the generator failure had resulted not from inadequate design, but from fundamental misunderstanding of electrical load characteristics under continuous operation. The burned windings showed heat patterns that indicated voltage regulation problems. The high-voltage, low-amperage system he had copied from industrial applications was inherently unstable when powering variable loads like scraper blade motors operating in changing soil conditions. Dutch Hendricks arrived at the project site before dawn on September 19th with a truck loaded with electrical components that LeTourneau had ordered from Pacific Gas and Electric's Industrial Supply Division. The replacement strategy was desperate but theoretically sound. Instead of replicating the failed high-voltage system, LeTourneau would rebuild the generator to deliver lower voltage at higher amperage, creating more stable power delivery for motor control applications. The electrical theory was untested in earth-moving applications, while the time required for complete reconstruction would consume days that the irrigation contract could not spare. The breakthrough came from analysis of the undamaged motor housings, which showed wear patterns that revealed how electrical controls actually functioned under field conditions. The blade elevation motors operated most efficiently when receiving steady current flow rather than the voltage spikes produced by the original generator design. LeTourneau realized that earth-moving applications demanded electrical characteristics opposite to industrial machinery. Instead of high voltage for power transmission, scraper controls needed high amperage for consistent motor torque, regardless of load variations. The discovery would revolutionize electrical earth-moving, but only if he could prove the theory with a rebuilt machine. Working 18-hour days through the final week of September, LeTourneau and Hendricks reconstructed the mountain mover around electrical principles that contradicted established industrial practice. The new generator produced 420 volts at 750 amperes, creating power delivery characteristics that matched motor requirements rather than transmission efficiency. The motor control circuits were redesigned with heavier conductors capable of handling increased current flow, while the electrical switchgear incorporated protective devices that prevented the overload conditions that had destroyed the original system. Every component was oversized for reliability rather than optimized for efficiency. The backup systems that emerged from the reconstruction represented innovation born from catastrophic failure. Dual generators provided redundant power sources, ensuring that single-point electrical failures could not stop operation entirely. Emergency manual controls allowed operators to adjust blade elevation and bowl extension mechanically if electrical systems failed, while heat-resistant motor windings incorporated insulation materials that could withstand temperatures that would destroy conventional electrical components. The rebuilt mountain mover was engineering overkill designed to function under conditions that would disable any comparable machine. The Irrigation District's patience expired on October 1st, with 240 acres remaining and autumn weather threatening to flood unfinished sections. Samuel Peterson arrived at the project site with legal documents prepared for contract termination, while James Morrison documented the reconstruction efforts with skepticism that bordered on professional disdain. Traditional contractors had begun mobilizing equipment to complete the leveling using proven methods, treating LeTourneau's electrical experiment as expensive confirmation of European engineering wisdom about American innovation's inherent unreliability. The rebuilt mountain mover's first test on October 2nd revealed the power of low-voltage, high-amperage electrical control. The blade motors responded with precision that exceeded the original machine's performance, maintaining consistent cutting depth despite soil condition variations that would have caused voltage fluctuations in the previous system. The telescoping mechanism operated with mechanical authority that demonstrated the superiority of steady current flow over variable voltage delivery, while the dual generator system provided power redundancy that eliminated single-point failure risks. The electrical controls that emerged from catastrophic failure were superior to anything LeTourneau had previously achieved. The coordinated operation of 3 electrical units during the final construction phase demonstrated earth-moving efficiency that traditional methods could never match. The rebuilt machines worked in patterns that maximized earth movement while minimizing transport time, with electrical controls maintaining grade accuracy within the Irrigation District's 2-inch tolerance requirements. The telescoping bowl systems loaded maximum capacity on every cycle, while automatic controls eliminated human judgment errors that reduced productivity in manual operations. The mathematical precision of electrical automation was transforming agricultural earth-moving from labor-intensive craft to engineering discipline. Morrison's daily observation reports documented productivity that challenged every assumption about earth-moving limitations. The 3 electrical units were completing 30 acres per day of precision leveling, rates that exceeded traditional crews by factors that suggested fundamental changes in construction capability. The grade accuracy achieved through electrical blade control eliminated the rework that consumed 20% of manual earth-moving time, while the coordinated operation of multiple units created efficiency multipliers that no combination of conventional equipment could achieve. The engineering establishment's dismissal of electrical controls was being contradicted by mathematical results that could not be disputed. The breakthrough moment came on October 8th when the rebuilt mountain mover encountered the same hardpan section that had challenged traditional crews throughout the summer. The low-voltage, high-amperage electrical system powered through the compacted earth layer with consistent force that manual operators could never maintain, while the blade elevation controls adjusted cutting pressure automatically to match soil resistance. What had been project-stopping obstacles for conventional equipment became routine operations for electrical automation, demonstrating technological superiority that extended far beyond simple productivity improvements. The final week of construction proceeded with mechanical precision that amazed even skeptical observers. The electrical units completed the remaining acreage with grade accuracy that met irrigation district specifications, while the coordinated earth moving eliminated the soil transportation inefficiencies that plagued manual operations. The telescoping bowl mechanisms had operated flawlessly through thousands of extension and retraction cycles, while the waterproof motor housings had eliminated the electrical failures that European engineers had predicted would make field automation impossible. The mechanical revolution that had nearly died in generator failure was achieving vindication through superior performance. The project's completion on October 28th represented triumph that transcended simple contract fulfillment. 640 acres had been leveled to irrigation specifications in exactly 30 days, including the week lost to generator reconstruction. The final cost of $4.50 per acre was less than half the expense of traditional methods, while the grade accuracy achieved through electrical controls exceeded anything possible with manual earth moving. Samuel Peterson's investment had generated returns that validated risk-taking in American innovation, while James Morrison's reports would carry news of electrical earth-moving success to engineering establishments throughout the eastern United States. The success of the irrigation project triggered an avalanche of orders that overwhelmed LeTourneau's Stockton workshop within weeks of completion. By November 1922, 17 contractors had placed deposits for mountain mover units, while the California State Highway Commission approved electrical scrapers for all future road building projects. The demand represented validation beyond LeTourneau's most optimistic projections, but it also created manufacturing challenges that threatened to destroy his company through success rather than failure. Building 17 Precision, machines with the handcrafted methods that had produced the original prototypes, was mathematically impossible within any reasonable time frame. The solution demanded industrial transformation that would either establish LeTourneau as a legitimate manufacturer or bankrupt him, attempting to scale beyond his capabilities. He purchased a 12-acre site on the outskirts of Stockton, complete with railroad siding access and electrical power sufficient for production machinery. The investment consumed every dollar generated by the irrigation contract, while the expansion plans required borrowing against future deliveries that existed only as signed purchase orders. LeTourneau was betting everything on his ability to transform workshop craftsmanship into factory production without compromising the precision that made electrical controls superior to manual alternatives. Dutch Hendricks supervised the construction of manufacturing facilities designed specifically for electrical earth-moving equipment production. The main assembly building incorporated overhead crane systems capable of handling 8-ton scraper units, while separate departments specialized in generator manufacturing, motor housing production, and telescoping mechanism assembly. The electrical systems required quality control procedures that exceeded anything used in agricultural equipment manufacturing. Every motor was individually tested under load. Each generator underwent 48-hour endurance testing, and the telescoping mechanisms were cycled through thousands of extension and retraction operations before approval for field installation. The manufacturing processes that emerged from LeTourneau's expansion represented innovation that transformed precision craftsmanship into repeatable industrial procedures. The telescoping bowl mechanisms required machining tolerances measured in thousandths of an inch, achievable only through fixture systems that maintained exact positioning throughout the manufacturing sequence. The nested steel sections were machined using techniques borrowed from railroad locomotive production, while the bronze bearing surfaces incorporated metallurgy knowledge that LeTourneau acquired through correspondence with engineering departments at major universities. The result was manufacturing capability that could produce precision machinery at scales previously impossible. James Morrison arrived at the Stockton factory in December 1922 as representative of Maritime Construction Company, which was considering licensing LeTourneau's electrical control systems for use on East Coast projects. Morrison's evaluation would determine whether electrical earthmoving remained a regional California innovation or achieved national acceptance among major construction firms. His inspection focused on manufacturing quality control and the reliability of electrical systems under extended operation, while LeTourneau demonstrated production techniques that challenged Morrison's assumptions about American manufacturing capabilities. The factory tour revealed manufacturing sophistication that impressed even Morrison's European-trained engineering perspective. The generator production line incorporated precision winding techniques that created electrical output characteristics specifically matched to earth-moving motor requirements, while the motor housing assembly utilized waterproofing methods that exceeded marine electrical standards. The telescoping mechanism manufacturing required metallurgical knowledge and machining precision that Morrison had previously associated only with locomotive or naval construction, applied to agricultural equipment that operated in conditions more demanding than most industrial machinery. The breakthrough that secured Morrison's endorsement came during field testing of a production mountain mover unit operating on a highway project near Modesto. The electrical controls maintained blade depth precision through soil conditions that varied from loose sand to compacted clay, while the telescoping bowl system loaded maximum capacity on every cycle without mechanical failure. The productivity data was undeniable. The single electrical unit was completing earthwork at rates that exceeded three-man traditional crews by margins that suggested fundamental changes in construction economics. Morrison's report to Maritime Construction would recommend immediate licensing of LeTourneau's electrical control technology. Samuel Peterson's investment syndicate expanded in January 1923 to include San Francisco banking interests that recognized the financial potential of electrical earth-moving equipment. The syndicate provided capital for factory expansion that would triple production capacity, while securing exclusive distribution rights for LeTourneau machines throughout California and Nevada. The financial backing validated electrical earth-moving as legitimate industrial innovation rather than experimental technology, creating market confidence that generated additional orders from contractors who had previously remained skeptical of unproven automation. The California State Highway Commission's adoption of electrical scrapers as standard equipment for all major projects created governmental endorsement that influenced construction industry attitudes nationwide. Highway engineers who had initially viewed electrical controls with suspicion were documenting productivity improvements and cost reductions that exceeded the most optimistic projections for automation benefits. The mathematical results were transforming electrical earth-moving from innovative experiment to engineering necessity, while established contractors who had dismissed LeTourneau's methods began inquiring about equipment availability and operator training programs. Abraham Grunauer's expansion of his earth-moving contracting business around electrical equipment demonstrated the commercial viability of automation that European engineers had declared impossible. Grunauer's crews, equipped with the latest mountain mover units, were underbidding traditional contractors by margins that forced industry-wide reconsideration of earth-moving economics. The German immigrant who had initially tested LeTourneau's first electrical prototype was now operating the largest earth-moving business in the Central Valley, built entirely around single-operator automation that eliminated the crew coordination problems inherent in manual methods. The technical refinements that emerged from factory production created electrical earth-moving equipment that surpassed even LeTourneau's original vision. The latest generator systems delivered power with stability that eliminated the voltage fluctuations that had caused early control problems, while the motor housings incorporated cooling systems that maintained consistent performance during extended operation. The telescoping mechanisms had evolved into engineering marvels that could extend and retract under full load thousands of times without requiring maintenance, while the all-welded construction created structural integrity that could withstand forces that would destroy conventional equipment. The validation moment came in February 1923 when the Engineering News Record published a comprehensive analysis of electrical earth-moving productivity based on data collected from projects throughout California. The magazine's technical staff had documented productivity improvements averaging 300% over traditional methods, while cost reductions approached 50% of conventional earth-moving expenses. The precision achieved through electrical blade control was eliminating rework that had historically consumed 20% of manual earth-moving time, while single-operator automation was solving the crew coordination problems that had limited traditional productivity. By spring 1923, RG LeTourneau Incorporated was producing one electrical scraper unit per week from the expanded Stockton factory, with orders extending 6 months into the future. The mechanical revolution that had begun as a sixth-grade dropout's vision of single-operator earth-moving had become an industrial reality that was transforming construction practices throughout the American West. The electrical automation that European engineers had dismissed as mechanically unsound was proving superior to manual methods in every measurable category, while creating productivity improvements that challenged fundamental assumptions about construction limitations.